It says from 2.6, but I think it was more from module 7 kind of stuff, right? Where you saw some, whatever, maybe it was 2.6. But in any case, below is the formal definition of a function. It's really just a nerdy way to say, for functions, remember every x value can only have one corresponding y value. You can't have, for example, in a set, you can't have the ordered pair 2, 3, and then also have the ordered pair 2, 10. Because, and we talked about this is like your input, right? Your x values are input. When you put it in a 2 and you get out a 3, that's good. But if you come back and you put it in a 2, and now comes a 10, it's like what the crap is going on right here, and then it's no longer a function, okay? And there's different ways to do that, both with equations and tables and mappings and graphs, but that's really what it comes down to. So this particular lesson is mostly about domain. So yeah, there's just a quick explanation that we saw about range as well. You know, now that I think about that more, I think it was 2.6 that we saw domain and range stuff, but I also assume no one really cares. But in any case, there's your domain stuff. Yeah, domain, a list of x values. We know we saw in the beginning there, sometimes that requires some of those fancy brackets, which are super awesome because they're so fancy and classy. When solving equations, we ended with one answer. Yeah, that was just like this one right here. This is the one-step equation. We did two-step equations, then multi-step equations. That's principle of equality stuff, in addition to distribution and combining like terms, okay? But in the end, we found only one value. Most of the time, we only found one value of x that would make the equation true. That means that there's only this one value in this particular equation in the domain. Now, later on, we saw absolute value equations that could have had two answers, and then you'd say, well, x could be maybe 3 or 14, I don't know. And then now you'd have two values in the domain. But we even saw sometimes where the equations had an infinite number of values. And there are different ways to express those, even if they're within some kind of interval. And there's that dreaded, awesome word that we remember, intervals, because they are coming back when we talk about domain. And so sometimes we're going to actually, oh, there it is. Oh, no, I was thinking infinite. Some of these we're going to have to describe with intervals, okay? Yeah, and with regular graphing, y equals mx plus b stuff, remember m is slope, b is the y-intercept. Hopefully you kind of remember that because the final's coming up. But there's an infinite number of x values. If you look at a graph, right? So let's pretend like these are good lines. That's an x-axis and a y-axis. If you drew some kind of line with y equals mx plus b, kind of thing, you got the y-intercept and then the slope is m. This, I probably should have put those arrows on there, but this line continues forever to the left and right. And remember, that's all we're concerned about with domain. That's our x values. So this would go from negative infinity, it would never stop, and it would go all the way to positive infinity as well. Okay, so that's kind of what we focused on, is seeing what values of x do work. Really, what we're going to be looking at today is values of x that don't work in the equations, right? Now, that doesn't mean we're going to include those in the domain. We only want to include values of x in the domain that make the equation true. Okay, but sometimes it's easier to figure out what those values are when you think about what x is not. Okay, so this is more of what's called indirect reasoning, like when it comes to logic and stuff like that, okay? So we're looking at everything that would not work, and then that kind of tells us in response what would work. I don't know, that can be kind of confusing, but we'll see some examples. Hopefully this would make sense as we see some examples here. And yeah, like I said, we're going to be using some interval notation, which is either one of these. Remember, if it's included, we use a square bracket. If it's not, then we use just regular parentheses. On graphs, the square brackets like this, that was the closed circles, and then the regular parentheses, those were the open circles, okay? And again, that's since we're only dealing with x numbers, we tend to use the horizontal number line like this one, right? Then you got positives to the right, negatives on the left. And then, yes, so for example, right, you could say, maybe we see in something like this, right? So maybe one's open, one's closed, and then just whatever's between those. And the domain is going to say, maybe the domain, the only values of x that would work in this particular equation, whatever it is, would work only in this interval. And then, yeah, set builder notation now. So we know it's always x is and such that x, maybe it's less than, maybe it's greater than, maybe it's less than or equal to or greater than or equal to, but usually includes some kind of inequality in here to demonstrate the interval that would work as well. On Canvas, usually all you got to do is type in this part, like this. Now, if you did, just by chance, if you did need to, the fancy brackets, they're on the, I don't know, they're close to the enter button right there. Yeah, and so that's the fancy brackets, but this line right here,
Yeah,
you know, X is such that whatever this symbol means, it's usually like one button above return. And I'm looking at my iPad, it's the same thing as my computer, which is, what do they call it, PC or whatever. Let's look at domain of root functions, okay? So even roots cannot have negative radicands. Remember the radican's on whatever's on the inside of the root. So if we see some kind of root like this, whatever's in here, and sometimes it's an expression, right? Like we see in that maybe be x minus 3, something like that. Maybe x minus 13, maybe 4x minus, whatever it is, okay? But the interesting thing about this is that your radicand, remember, we can't have a negative radicand because you wouldn't want a negative area for a square. Or you could say, well, what number, let's look at an example here, okay? Let's go back. So if we said, we're going to take the square root, let's make it, well, let's actually start with 9, just 9 for now, okay? So this is really asking what number times itself is 9. And then we would know that's 3. And if you don't, your calculator does, okay? Now, if we put a negative on that, the question is, what number times itself is negative 9? Now, again, one of the common mistakes while we're getting used to this stuff, and we did just finish Module 7, so students will say it's negative 3 times negative 3, but that's not negative 9, that'd be positive 9. Remember, they have to be exactly the same number, and of course 3 times 3 is positive 9. So this is where we say, right now we're just saying that the answer is not real or DNE kind of stuff, right? But when it comes to the domain of these root type functions, what we're saying is that whatever the radicand is, it has to be greater than 0. So if we looked at this example, this first one that we started with here, I don't really care about the radicand so much, I don't care about the root so much as the radicand, the inside right there, right? So that's when I say, I'm just going to take the inside of the root, the radicand there, 4x minus 13, and I just know it has to be greater than or equal to 0. I can solve this inequality, like we saw on the last slide. I can put that into set builder notation. I could put that inequality on a graph, and then I could write the interval for that inequality as well. I'm not going to solve this one because we're going to have plenty to solve. But this is essentially what we're doing. Just take the inside of your radical, in this case the root, and just make it greater than or equal to 0. Now remember, this is only when the index is either not shown or if it's even. If it were an odd index, then none of the inside matters. That you could have whatever value of x you want, and you could pull out whatever the root is. Okay, again, this is only applying to even roots. All right, find the domain in interval notation. Okay, no problem. Now I'm going to put the graph on this one just to give us a little bit of a reminder on that stuff. Not just because it's going to help me to make the interval, but it should help us with stuff that may be on the final, right? So once again, all I'm going to do here, let's take a closer look. I'm just going to take the inside, this 3x minus 4. And I know that it has to be greater than or equal to 0 in order for us to have any real values out of this radical, this square root, okay? So this right here actually does represent the domain, right? But I do want to solve this so I can figure out exactly what values of x would make this work, okay? So here's where we come into some principles of equality. Right here I'm going to add 4 to both sides. That's going to zero that out, drop my 3x, which now is greater than or equal to 4. And then finally, with a little bit more space, I would divide both sides by 3, okay? So I see x must be greater than or equal to 4/3. That is the domain. Now, if this is set builder notation, maybe you got some fancy brackets, s then a 2, to close them, to 2, then an s, and you say x, such that x is greater than or equal to 4/3. Now, this is nice, and it was fun to do, but If that coefficient were a negative, remember with your inequalities, if you ever had to divide or multiply both sides by a negative, it would have flipped that inequality, which could happen now, just like it has happened in the past, okay? So this is set builder notation, but it said it wanted interval notation, right? So let's make sure that we put this in interval notation. And again, just as a nice review, let's look at the graph on this one. So right in the middle, I'd have 4/3. To the left of that would be 3/3, and then to the right would be 5/3, okay? This one is x is greater than or equal to 4/3. It's equal to 4/3, could be. So I got a closed circle there at 4/3. This one is eating the x, which means that the line should go to the right. And now that's all that I would need from the graph, but now I need the interval notation starting at 4/3, which is included. So I got a square bracket there. This goes all the way to infinity, which is never included. So there at the bottom, we have square bracket 4/3, and then it goes all the way to infinity with closed parentheses. That right there is the interval. That's the domain. And yeah, you can say domain with that kind of stuff, but either way. Question. So right here, I always set it up with the 0 on the right side of the inequality. And it should always be opposite of the, I'm saying opposite, it should not eat the 0. Or you could say that it eats the radicand, right? So another way to set this up would have been 0 is less than or equal to 3x minus 4. And that would have worked too. If you solve this, you'll get the exact same inequality, just maybe your x is on the other side. So you'd end up with x here, but 4/3. But again, it would be eating the x like this.